All right, so I'm going to record you a proof of this theorem here using the combination, which I tried to do in class. I'm going to give you two proofs actually, but I feel like this triangle here reiterates better what we're doing. It says if I want to look at the n+1 entry, I go back one and I look at the previous two. So I can add these two together to get the next row's entry of Pascal's triangle. And we know the entries are always one. So that helps us fill in everything in between. Okay, so let's prove this. So n+1, choose k. This is a proof that uses what's called a combinatorial theorem, a combinatorial proof, because we're counting how many ways we can do this. This counts how many ways to choose k elements out of n+1. So how many ways choose k elements? I'm going to make a set A have n+1 elements. So it's 0, 1, 2, up to n. Notice there's n elements here, so I add 0. That's n+1. So n+1 choose k is how many k element subsets I can make out of A. Okay, so that's what that is. Now consider each subset, k element subset. It has two things that can happen. Either 0 is in the set or 0 is not in the set. Okay, so for each k element subset, if 0 is in the set, then there's k-1 remaining elements, because one of them is 0. And if 0 is not in the set, there's k remaining elements. Right? And in each case, the k remaining elements are of the set A, set -0. Because if 0 is not in the set, well, there's k elements of which are not 0. And if k is in the set, there's k-1 elements of which are not 0. So the ways to count that is, so this is both remaining of n elements. The remaining elements are 1, 2, up to n, right? Because 0 is not in this set here. So how many ways are there to pick the remaining elements? Here there are n, choose k-1. We're choosing k-1 elements to match the 0. So we have 0 in this set and k-1 remaining elements. And in this set here, we have n, choose k, because there's 0 is not in the set, but there's just k elements in our set. So this accounts for all possibilities of each subset of this set. So the resulting way of counting is saying, hey, if I count the two ways that I can add my subset, it's another way to count k element subsets of n-1. So it's a combinatorial proof. It's also in the textbook if I explain that well. But the really cool thing about these kind of proofs is there's often many ways to do it. So I'll show you also a algebraic proof. So this is what we were doing in class. Okay, and we can count things in ways and it's the same thing. So n+1 choose n plus factorial and minus k factorial, k factorial. Okay, so that's something we can compare against. And choose k is n factorial. Oh, I did something wrong up here. And then k minus 1 n factorial n minus k minus 1 and k minus 1. And that's the same as n plus 1 minus k. So what I'm going to do with these two is try to find a common denominator, both these. So common denominator I can think of is k factorial here, n plus 1 minus k factorial here. So to get this denominator, I have to multiply the top and the bottom of this one by the additional n plus 1 minus k term, which is what we have here. But to get to the k factorial term, I have to multiply the top and the bottom by k minus 1. Sorry, not k minus 1. K. So that this is the same as this. And this is the same as this. Okay, now I have a common denominator and I can add these two together. And that gives me n plus 1 minus k, n factorial plus n factorial k. If I distribute this into there, keeping that together, I get n plus 1 n factorial minus n factorial k plus n factorial k. So those cancel. And so now, after doing arithmetic, we say that's the same thing as n plus 1 factorial. So the sum of these two is the same as the left-hand side. So we have proved question 1 in 2 different ways. Question 3, I'm going to get you guys to do. You can prove that using algebra. Go the algebraic approach. And it shouldn't be too bad. Okay, the other theorem from this chapter, which we won't prove, but we're going to use it, is the binomial theorem. It's very widely used in anytime you're dealing with polynomials where you're doing a power. You can find out the sum, in which the sum means, I'll do it down here, means I do n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, so on, up to n choose n, x to the 0, y to the n. So if I want to find out what x plus 2 to the 5th power is, the binomial theorem says I do 5 choose 0, 5 choose 1, 5 choose 2, 5 choose, I need more room. 5 choose 3, 5 choose 4, 5 choose 5. And I go x to the 5th, y to the 1, x 4y squared, x cubed, y cubed. Oh, y to the 0 here. Y to the 1, y2, it's 2y cubed, it's the 4th y, it's the 1, y to the 4th, x, the 0, y to the 5th. Add those all up. And I should put, instead of y in there, in this case, I have 2 as my y. Okay. So this is 1x to the 5th times 2 to the 0 is 1 plus 5 x to the 4th times 2. I don't know what it is. 1, 1, 1, 2, 1, 1, 2, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, so this is the row I'm using. So 5 choose 2 is 10 x cubed times 4. 5 choose 3 is 10 x cubed times 8 plus 5 choose 4 is 5x to the 16th plus 1 times 1 times 32. So this polynomial becomes x to the 5th plus 10x to the 4th, 40x cubed plus 80x squared plus 5, 16 times 5 plus 80x plus 32. So now I've expanded that polynomial, which is much preferable to actually multiplying something out many, many times. All right, so that's the rest of 3.8, 3.7, 3.6. So you can finish the homework for sections up to here. All right, we'll see you next Monday, and good luck, Ellie, on your games. Good luck, Ellis, with your kids.